chain rule. That is the formal definition of the chain rule. If we're going to differentiate u to the power of n, where u is some function of x, then the way we do it is we differentiate as normal, n, u, n minus 1, but then we also times it by whatever the derivative of that function is. Personally, I find that a very confusing thing to remember. No, this is how we do it. We do it like this. Bring down the power, lower the power, diff the inside, or anarchy. The chain rule is anarchy. Because what is anarchy? That's when you bring down the power, okay? So you bring down the power, but you really want to demoralize them, yeah? You really want to demoralize them, so then you throw them on the ground. So you bring down the power, then you lower the power, because you throw them on the ground. Diff the inside, you can think of it like a balloon. Right? Now, if that balloon is starting to contract, what happens to the air inside? It starts being expelled, yeah? So when we've chucked them on the ground and we're kicking them or whatever, and we're making the guts expel, what we're doing here is we're getting what's inside the parentheses and we're expelling the derivative. Okay, let's do it and show you what I mean. Here's the question that we did before when I said, at this stage we'd have to expand it out in order to do it. And the reality is, for something where the power's that low, I probably would expand out anyway. But here's what we're saying. Bring down the power. 2 comes to the front. Lower the power. I go to 1. Now, you get inside, expel that derivative. 2 gets expelled out, and there's my answer, which was the same as the one we got before, it's just factorised. Bring down the power, lower the power, diff the inside. Remembering this way, I always find I can say it as I write it, and then I know exactly what I'm doing. Bring down the power, I'm writing that number, lower the power. The chain rule is really good because now I don't have to actually expand out 3x minus 4 to the power of 7. That takes a long time. Bring down the power, 7. Lower the power, 6. Expel that derivative. 3. 7 3s are 21. Got my answer. X squared minus 10 cubed. Bring down the power. 3. Lower the power. 2. Expel the derivative. 2x. Oh, there it is. 6x. X squared minus 10 to the power squared. I'm not going to bother expanding it out. That's my answer. Ooh, 5's out the front competing. That's all right. When we bring down the power, we just multiply the 6 with a 5 and we get 30. Bring down the power. 5 times negative 2, negative 60. This is the chain rule. This is also implicit differentiation. It's all the same thing. But you see, if we've got a function written in terms of its parametrics, sure, I could recombine this and come up with what the function is and then go and differentiate it. But I don't have to. I'll just differentiate each piece. I'll find dx to t, that's 4. I'll find dy to t, that's 4t. I want dy dx, you see, because derivatives are a rate of change. What are rates? Rates are fractions. You can think of them like fractions. They're not really fractions, but you can think of them like fractions. And so it's like the t's are cancelling, if you like, and you end up with dy dx. 4t times a quarter, t is my answer. Okay, it's in terms of the parameter, but that is the derivative. If I wanted it in terms of y of x, then all right, t is x on 4, there's my derivative. Dy dx is x on 4. Okay, let's add that exciting one into the mix.